Alright, so in this video, we're going to go over the core problems in investigation 3.3.1. So one way to think about an equation is like a balance scale. So you notice that if I drag a blue tile onto the scales, it drags it down. So moving a blue tile drags it down. And the opposite of a positive is a negative. Notice that when I drag a red tile onto the scales, it pulls it up. Giving it like a balloon. Instead of weighing it down, it pulls it up. So a red tile moves it up. If I want to figure out the weight of an X tile, what I can do is I can keep placing tiles on the other side. So 2 and 3. And it looks like it takes 3 tiles to balance out an X tile. Okay. So the idea behind solving the equation is we have two goals. One is that we're trying to get X by itself, and the other is to make sure that the scales are balanced. So whatever you do to the equation, both sides have to stay perfectly leveled. Okay. So moving on to B part 1. So here, right now, we have the following equation, x plus 3 equals 8. And right now, x is not by itself. It's surrounded by these extra tiles. So what I need to do is I need to get rid of these 3 by dragging them off the mat. And notice that when I subtract 3 on the left side, it's no longer balanced. This right side weighs more. So to keep it balanced, I need to drag these tiles to the other side. I also need to remove 3 tiles on the right side. So whatever I do to one side of my scales, I need to do to the other side. In this case here, I'm subtracting 3 from both sides. So after doing that, I see that one X tile weighs the same as 5 of these squares. So X equals 5. So how do we isolate the variable when X is being added to? Right? We can subtract the same amount of tiles on both sides. Right? And it has to be the same amount in order to keep it balanced. Right, B part 2. Right now we have x and 5 negatives, or x minus 5 here. So another way we can get rid of tiles is by adding in its opposite. What it will cancel out with these 5 negatives would be 5 positives. So let's drag in these 5 positives. And notice that when I overlap them, they cancel out. So to get rid of these minus 5, I can add 5. But after adding 5 to one side, notice that it's no longer balanced. So I need to add 5 to the other side as well, plus 5. So after adding plus 5 to both sides, I see that one X tile weighs the same as 9 of these squares. So X equals 9. So another way, if things are being subtracted, I can add in opposite tiles in order to cancel out everything next to X. So essentially, since these are all canceled out, it's like having X by itself. All right, B3. So here, I have X divided by 3. So what does it mean when X is being divided? So instead of being a full X, so if I look back here, a full rectangle piece looks something like this. So instead of having a full X piece, notice that I only have a third of an X. Notice that it's broken down to a fraction. So when X is being divided, it's like having a fraction of X. So I don't have the full rectangle, only have part of it. So I know that a third of an X equals 2. So if I drag in another 1/3, notice that now I have 2/3 of these X's. If I drag in another piece to balance it out, I need 2 more. Okay. And if I want to complete one full X, notice that it now makes that rectangle. Do you see it's the same size as the full X back here? So it's now the size of a full X. If I want to balance this out, I also need 2 more. So what's happening when we keep adding the same parts over and over? Right, we can think of this as I have X over 3 plus another X over 3 plus another X over 3. And what's another way to represent repeated addition? You can think of this as I have X over 3 times 3. So I'm repeatedly multiplying. I'm timesing it by 3. So here I'm multiplying by 3. I'm adding the same parts over and over again. I'm tripling whatever I have. And notice over here I have 2 plus 2 plus 2. That's kind of like 2 times 3. I'm tripling whatever I have. This is like having 2 times 3. So I'm tripling both sides. So a third of an x times 3 parts, I complete my full rectangle. And then 2 times 3, I get 6. So how do we solve when x is being divided? We can multiply on both sides so that we have 1 full x. Okay. Here is B4. So how do we solve a problem when we have multiple x's? So right now we have 4x equals 12. Or we can think of 4x as having just more than one x. I have 4 of these. So the way we can solve this is that we can sort these out into equal groups. So since we have 4 of them, notice that we can split these up into 4 sections. 3, 4. But if I sort these into 4 groups, I need to also sort these into 4 groups. So mathematically what's happening is, when I have multiple x's, when I have 4 x's, what I need to do is I need to divide it into 4 separate sections. Right? And if I divide this into 4 sections, this also has to be divided into 4. So divide into 4 sections, divide into 4 sections. So how much is 1x? So I see that one of these tiles weighs the same as 3. So when I divide it into 4 sections, this part has to equal that part. So x has to be 3. So what does it mean when x is multiplied? It means we have more than 1x. And the way we solve it is we have to divide them into equal size groups. Okay. And finally, for the last one, here we have negative x equals 4. So again, the goal when we're solving an equation is that we just want normal x. We don't want negative x. So what we can do is we can flip it over. As mathematically, that's the same as multiplying by negative 1. I'm flipping the sign. A negative times a negative is a positive. But if I flip this over, I need to click on these empty spaces here and flip these over. So I also need to multiply this by negative 1. So 4 times negative 1, I now have negative 4. So how do we solve a variable when x is negative? We can multiply by negative 1 to flip the sign. Okay. So to summarize these questions, right, we have these 3 questions, question 1, 2, and 3. So why did we either add or subtract tiles to the scales? We add or subtract so that we can cancel out everything next to x to get it by itself. When we have a fraction, why do we multiply? So the reason why we multiply is that we're trying to get one full x, right? Here is only a fraction of an x. By multiplying, we complete that full rectangle. And when we have multiple x's, like 3x, why do we divide? We're trying to split them up into equal size groups. Okay? So those are just some of the reasons why we do certain math operations. For section C, here is going to be a multi-step problem. So it's going to take a few steps in order to get x by itself. So let's go over these problems real quick. So right now I have 2x plus 5 equals 11. Our first step is that I need to subtract 5 to get the x's by itself. Notice that it's no longer balanced. So whatever I need to do to one side, I need to subtract 5 tiles from this side. So 2, 3, 4, 5. I have 5 tiles being subtracted, minus 5. So what I'm left is, after taking away 5, I still have those 2 x's. And over here, 11 minus 5, I have 6. So what's left to do with multiple x's? Like we talked about earlier, I can divide these into 2 different groups. But if I divide those, I need to also divide these into 2 different groups. So after dividing on both sides, I get divided by 2, x equals 3.